Okay, let's go ahead and get started. My goals today are twofold. First, I would like to help you understand that tutorial homework, tutorial number 3, the homework that's due on Monday. And I would like to encourage you to do that homework before you go and take the exam, so that you are ready. The second goal today is to just work lots of problems to get you feeling more comfortable with these ideas. And so we're not going to introduce any new concepts. We're just going to practice the old concepts that we've already seen. By way of announcements, come on. There we go. I will be holding a review session tonight at 7 o'clock in this room. And I'll just answer your questions, and that will be recorded and posted to YouTube for those of you that have other commitments in the evening. The 2 sample exams are representative of the types of problems and the difficulty of the problems that you'll be able to expect on your exams. And the equations on those sample exams are identical to what you'll have on the front page of your exam. That's the way I just copied and pasted them. Okay, so those are the equations that you'll have. Are there questions concerning the exam before we launch in? Yes, sir.
Multiple choice and open-ended?
I do not have the teaching staff needed to do any open-ended questions. There's just too many of us, 560 students. So there'll be 26 multiple choice questions. Most of them are worth 4 points each. Some are worth 3, some are worth 5, depending on the difficulty. Okay. Would someone be willing to give us an opening prayer this morning? Get us started. Thank you.
Heavenly Father, we're grateful to be here today. Grateful for Dr. Francis for bringing his light to us, and please help us to be able to have that spirit as we learn some more physics today and throughout the rest of our classes. We say this in the name of Jesus Christ.
Amen. Thank you. Okay. In that tutorial, you found that there were 2 different flavors of charged plates. There were insulated plates, or sometimes called isolated plates, in which we charge them up, usually with a battery, and then we take the battery away. And the thing that is unique about this setup is that that charge is stuck. It can't get off the plates. There's no path for it to go anywhere else. And so that means that if I were to move these plates closer together and ask, well, how does that change the situation? I know that the sigma has to remain the same. Like I said, it's stuck there. And the other thing you know is that when you have 2 plates or 2 sheets, same, that are equal and opposite like this, the electric field between the plates depends on that sigma. And so that means if the sigma doesn't change, the electric field doesn't change. No matter how close I get them or how far apart they get, that electric field is going to stay the same. Does that make sense? The sigma makes the electric field, not the plates. Okay, the sigma, the charge. Now, what about the voltage? Well, if you think about voltage as how much Verk, the voltage between the plates is how much Verk I would need to do to take 1 Coulomb and push it from the negative plate to the positive plate. Well, if the electric field stays the same, I gotta fight the same. But here I don't have to fight as far. And so that means the voltage between the plates gets smaller. The E field stays the same, but the distance between them gets smaller. And that means the voltage between the plates gets smaller. Okay? Now, the other flavor is we charge them up with the battery and we leave the battery connected. If it's a 6-volt battery, we learned in the tutorial that that's got to be 6 volts between the plates. And that's the battery's job. It keeps the positive plate 6 volts higher than the negative plate if it's a 6-volt battery. And it does that through chemistry, which we can't possibly understand in this building. Okay? Now, we found last day that just like elevation, this voltage is independent of path. And so I can prove that this voltage has to be 6 volts by taking this path through the metal plate. We know that the electric field inside of metal is 0. And so that means I could move my 1 Coulomb through this plate and up through that wire with no effort. It takes no work, no Verk to move a Coulomb through metal because there's no field to fight. Now, in order to get that 1 Coulomb from the negative terminal of the battery to the positive terminal of the battery, I have to do 6 joules of Verk for each 1 Coulomb. Okay, so the voltage difference there is printed right on the side of the battery. It says, you know, this is a 6-volt battery. The voltage from the negative terminal to the positive plate, 6 volts. Now, again, I'm in the metal, and so I don't have to do any Verk to go there. And so that means the voltage between the plates has to be the same as the battery. Now, let's talk about what that means when I move those plates closer together. Okay? Well, now it's not the charge that is constant. It's not the charge that is fixed. It's the voltage between the plates. That's got to be 6 volts. That's the battery's job. Well, how does it do that? How does it do that? Well, if I have to do the same amount of Verk to get 1 Coulomb from here to here, as I did from here to here, if I'm pushing a shorter distance, I better be fighting a stronger field. And so that means the electric field has to increase in order to make the voltage the same. Now, here's the equation again, but you'll notice that this time I kept the delta V the same size. And when D got smaller, that meant E had to get bigger to compensate, okay? Very, very different, in fact, opposite of what we saw with the isolated or insulated plates. They act completely differently. Now, if the electric field got bigger, that means that the sigma that causes the electric field had to get bigger. Well, how can that be? Well, it can be because the sigma's not stuck anymore. It's got a path through that battery. And so what the battery does to increase the electric field is as I'm moving these plates closer together, the battery drags electrons off of this positive plate and puts them on this negative plate to make it more negative and this more positive to increase that field. Okay, if I were to take, this is just a thought experiment. If I were to take a little flashlight bulb and put it right here or right here, doesn't matter, okay? As I was moving the plates closer together, that bulb would light up. it would light up because electrons would be flowing from one plate to the other. And as they went through that bulb, it would cause it to light up. And we're gonna learn about that starting on Tuesday next week. That's my favorite part of the class is electric circuits. You're gonna love it. It's great. Okay. Now, questions? You very much need to know the two different flavors. And when you get to an exam question, you need to ask yourself, what flavor do I have here? Because if you know, use the things that we learned about one flavor for the other, you get exactly the opposite of the right answers. Yes, sir.
What part of the sigma is the part that increases?
I'm sorry?
What part of the sigma is the part that increases? All of it?
Well, remember sigma is how much charge I have per unit area. It's a thickness of, you know, if I'm painting charged paint, it's how thick do I make the paint? And so when the electrons come over, they just spread out to make it bigger everywhere. It's always going to be a uniform sigma. Did I answer your question or did I not understand?
So you're saying same charge, but just more of that charge? And
I'm saying that if I started out here with 3 coulombs, 3 positive coulombs for every meter squared, and 3 negative coulombs for every meter squared, after I push them together, I'm going to have 5 positive coulombs for every meter squared and negative 5 coulombs for each meter squared. That makes sense. Yeah. Okay. Now, in your textbook, there are 2 examples in chapter 17, 4 and 5. Example 4 and example 5. And I'm going to contend that they are pretty much exactly like your tutorial homework. Okay. And I'm going to start with example 5. And you know, if it were a perfect world and I got everything that I wished, okay. If it were that world, you would all have read this example. Yeah, okay. So I wish it were a perfect world. In this example, we start with insulated or isolated plates. This one is positive and this one is negative. I'm going to use green for positive and purple for negative. Now, we're going to also look at plates that are exactly the same amount of charge, but closer together. But A and B are the same distance apart. They're just locations, they're just addresses. There's nothing at A or nothing at B yet. Okay, they're just addresses. And in that example, we have 2 races. The first race is we take a proton at A and let it go. And it races off to B. It wants to be closer to that negative plate. So it races off to B. And it's going a certain speed that we calculate in that example, but we don't really care what it is. The question is, if we had released that proton over here at A, when it got to B, would it be going faster, slower, or the same? See if your neighbor knows. See if your neighbor can predict what that would be like.
I think it would be going faster. I guess it would depend. It's what flavors we're dealing with, battery or insulated. If we were dealing with insulated, then it wouldn't matter. Yeah. Yeah. Battery.
Oh.
Okay, the key is those two buckets. One filling and one draining. Speeding up is gaining kinetic energy. Well, that energy has to come from somewhere. It comes from the electric potential energy bucket. And so the question is, which of those protons had the bigger change in electric potential energy? The bigger drain, because that's the one that's going to speed up the most, right? Now, if we look at that, since they're both protons, the test charge is the same. So what we really care about is which proton went through the most volts. And you know that if we're going from the positive plate to the negative plate, this voltage change is going to be negative, okay? Because when you take that negative voltage change, if I take a negative voltage change, a positive charge on a proton, and that minus sign right there, meaning it's a zero-sum game, that gives me a positive change in kinetic energy. Now, the key here is that the electric field between these plates doesn't change. That stays the same, okay? The other thing that stays the same is the distance from A to B. If I want the voltage difference from A to B, this has to be the distance from A to B. The distance between the plates got smaller. I don't care. That's not the voltage I'm looking for. I'm looking for the voltage from A to B. And so if the electric field stayed the same and the distance stayed the same, the voltage difference stayed the same, it's a tie. It's a tie. See if your neighbor followed that.
Yeah. Yeah.
Okay. Now, in this example 5, there was another race. And this time, we took an electron and let it go right near the negative plate and watched as it raced across to the positive plate. And we calculated how fast it was going right before it rammed itself into that positive plate. And then we asked the question, well, what if we had released that electron here and watched it ram into that positive plate? Would it be going faster, slower, or the same when it got across to the positive plate? Now, again, what matters is how many volts did it race through? And if we go back to this equation, now we're not interested in the voltage difference from A to B, because this race is going from the negative plate to the positive plate, okay? So we want the distance from the negative plate to the positive plate. The electric field stays the same, but the distance between the plates got smaller. And so that means that when this electron rams into that plate, it'll be going slower. It had a smaller change in voltage. Talk to your neighbor.
If it's going from the plate, yeah, they're closer together. Because the difference, the work that's required will be smaller.
Okay. Now,
Electron from.
what does this have to do with your tutorial homework? Is that any different? That looks like your tutorial homework, doesn't it? Where you put a neutral metal slab in between the plates. Now, let's go back. I'm going to give you an analogy here. The administration comes and they say, you know, we can't afford to keep all these buildings heated and the lights on and everything for the whole 17 weeks of the semester. So what we're gonna do is we're gonna drop 3 weeks off the end of the semester. And we're going to tell the professors that they can't require any more work each week. You have to have the same sort of a workload each week. Well, at the end of the semester, are you gonna cover as many topics as you used to? No, you're not gonna get as much total work done in that semester. Now, in this case, they say, hey, we're gonna be open the whole 17 weeks, but we're forcing you to take a 3-week spring break, we're gonna call it, only it's a really super break, okay? And we're gonna forbid you from doing any schoolwork during those 3 weeks, only suntan, okay? And oh, the professors can't require any more work of you each week that you're working. It's the same thing. You're going to get less done during that semester. And that's what the tutorial homework is about. The electric field out here where there's no slab stays the same as it used to. But inside the slab, I have to have 0 electric field. That's what we learned last week. It has to be 0. And so that means when I'm trying to bring a 1 coulomb from the negative plate to the positive plate, that's how I think about voltage. I got to fight all the way to here, and then it's just free. I'm on the beach. And then I got to fight all the way there. So I got to do less fight than here. Here I've got to fight all the way across. Here I've got a spring break. I don't have to fight here. See if your neighbor followed that analogy.
You know, I don't understand why it works. Yeah, but I understand.
I guess I'll go to the negative side.
Okay,
Yeah.
so I did that exercise first because that's the first problem on your tutorial homework. So now let's look at example 4, which happens, of course, earlier in the textbook. But this is the one that's like the second big problem on your tutorial homework. In this case, we've got those plates again, but now they're hooked to a battery. Make it 6 volts, 12 volts, whatever you want, okay? And we have the same 2 races. We take a proton from A to B, and we take an electron from the negative plate to the positive plate. So let's first of all, and again, any gain that I get in kinetic energy, that's what speeds it up, has to come from a loss of electric potential energy. And that means the voltage that it passes through, the voltage difference is what I mean, is going to determine how fast it's going at the end. So this time, let's talk about the electrons first. The electron race from here to here versus here to here. Well, what's the same is the voltage between the plates, okay? And what that means is that if the voltage between the plates has to stay the same, the electric field can't stay the same. As the distance between the plates gets smaller, my electric field has to get larger, okay? If this has to be equal to that, say 12 volts, making that smaller means this has to get bigger, okay? So what does that mean for the electron race? It's a tie. It's a tie, okay? They're going to be going the same speed when they ram into the positive plate. But now the proton race is not a tie. Because even though the distance between A and B stays the same, the electric field between A and B doesn't stay the same as we move the plates closer together. So now, because the distance stayed the same, but the electric field got bigger, my voltage between A and B got bigger. And so that means that this proton is going to be going faster when it gets to B than this one. Now your gut tells you that because we're racing the same distance and we're being pushed by a stronger field. If you go back to what you learned in physics 105 and think about speeding someone up on a skateboard, if you push harder on them, they're going to speed up more. Okay. Now, again, what does that have to do with your tutorial? How? Is that any different? Is that any different? Okay. Now, back to the analogy, the administration comes and says, hey, we can't afford to keep the buildings open and heating and lighting for 17 weeks. So what we're going to do is we're going to shorten the semester by 3 weeks. But this time we're telling the professors, you have to cover just as many chapters as you used to in the semester. You can't short shrift them on their education. What does that mean about how much work you're going to have to do each week? Yeah, it went up. You're going to have to really work hard during the remaining weeks. Well, this is just the same thing, but now they say we got a 3-week spring break in the middle of the semester and you can't do any work during that spring break. Oh, but the professors have to cover the same number of chapters during the semester. And so that means that I'm going to have to, if I had to do 6 joules of Verc, well, we said it was a 12-volt battery. If I have to do 12 joules of Verc to get 1 coulomb across, I have to do 12 joules of Verc to get 1 coulomb across. But I'm not fighting anything here. So that means I have to fight stronger here and here than I was fighting there. Check again on your neighbor. Do a buddy check.
I would too, and then I realized that the first problem we did, the reason why it's different is because they have the insulators, and the insulators don't change, or the voltage can change, but with the battery, no. So the distance or the. But like insulators, like
So you're using this one.
it doesn't. It's even if it's
Okay.
like.
I have a practice problem for you. Let me hand that out.
In a battery.
On the back of this sheet, I put the midterm preparation sheet that I posted on Monday. I just didn't want to have a blank sheet on the back of anything. Didn't want to waste the paper, so help me. Well, you're not going to help me. No. Who do I have over here? Okay. When you get this, start looking at the problem. Okay, does anyone still need one? Everyone have one? Okay. We still need some up front. We walked right past the front row there. Okay, this problem has two parallel plates and they are connected to a battery. So that's the first thing you look at when you've got a parallel plate problem is, is the battery there or did we use the battery to charge up the plates and take it away? Is this an isolated case or the battery connected case? This one's the battery connected case. Now, the first part of this problem, we are told that there's a particle of mass m and charge q, and it's been fired somehow out of a gun at some horizontal velocity halfway between the plates. And the particle, we find, moves at a constant speed along a straight line. Now, thinking back to Physics 105, what should be going off in your head right now? Ding, 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 ding. When we hear constant speed, straight line, what does that trigger? Yeah, zero acceleration. And we have zero acceleration when we have zero net force. And that means that a free body diagram for this particle had better scream balance, had better scream zero. And so let's draw that free body diagram, okay? I have two forces. We're told in the problem that we should not neglect the gravitational effects. This thing has a significant mass, and the weight force is always down towards the center of the earth, okay? Now, the only other force acting on this is the electric force. And if that electric force is up, it will balance the weight force down. Now, we want to know whether this particle is positively or negatively charged. And we had a whole lot of people on this exam question not know. How can I know, Greg? That's impossible to know. That is unknowable. Okay? That is unknowable. Well, that's not going to earn you very many points. The reason they weren't able to answer this is that they didn't understand this symbol. And we've encountered it before. It's just a symbol for a battery. And for reasons that have nothing to do with physics and everything to do with tradition, this is always the positive terminal, okay? The long line is always the positive terminal. The short one is the negative terminal. That's just the way it's been done for hundreds of years, okay? Before I was born. Yeah. Okay. What that means is that if I were to draw my electric field lines, they're going to go from the positive plate up here to the negative plate down there. And so my field lines are going to be parallel to each other. Okay. Now, if I look at that equation in the middle here, if my force is up and my field is down, what kind of test charge do I have to have? Negative, okay, negative. And so this is going to be a negative test charge. Does that make sense to everyone? Okay. Good. Now, it says to draw a free body diagram for the particle when it's at point P. We did that. And label the vectors accordingly. I guess we didn't label this vector. This is the electric force, and it would be by the plates on the particle. Okay. Now, in part C, we're told this time, let's leave the plates where they were, but this time let's fire that particle a little bit closer to the negative plate. And we want to know what's going to happen. Is it going to follow that straight line, or is it going to veer up, or is it going to veer down? Tell your neighbor real quick what's going to happen.
I don't see. This is one. I think it'll stay. I think it'll be straight. If the particle doesn't change its mass, so it's gonna be bound.
Okay. I hope what you told your neighbor is that the electric field between two plates, equal and opposite, is uniform. I've got the same strength electric field here as I do here, as I do here, as I do here, everywhere between those plates. And so that means if this is the same, and this is the same, then that means that this is going to be the same. I should have drawn that in red. Okay. Now, if I've got the same electric force up and I've got the same weight down, my diagram's still balanced. I still have zero acceleration. It's still going to go at a constant speed in a straight line. It doesn't matter. Okay, it doesn't matter. Okay. Now things do matter. Now we're going to take that bottom plate and we're going to lower it. We're going to drop it down. We're going to increase the distance between the plates. And now, if I bring that negative plate down here, whereas I used to have some distance d, now I'm going to have some bigger distance d. What happens to the electric field between the plates? It gets smaller, okay? How do we know? By the end equation. If I go delta V from negative plate to positive plate is equal to the electric field strength times the distance between the negative plate and the positive plate. Well, the voltage has to stay the same because it's hooked to a battery. That stays the same. But if I make the distance bigger, the electric field has to get stronger. What that means is that if this gets small, wait, did I say stronger?
Yeah.
Is that what you heard?
Yeah.
I will testify in court that that's not what you heard, that you are all lying about me and trying to besmirch my good name. The electric field gets smaller. That's what I meant. Okay, smaller. Now, if the electric field now gets smaller, this force gets smaller. And now my free body diagram is no longer balanced. Now it screams down. And so that particle is, now it's going to follow some path like that, which is what we saw in 105 when we had a net force down. It was similar to free fall. Okay, check again on your neighbor real quick.
Because the force is smaller now. Because the field changed, the force also had to change. So it became smaller and the weight force still stayed the same. The weight force is more than the field, so it's gonna. I just. Yeah, for the.
I've only been in court once. I was asked by a lawyer to be an expert witness where physics was involved, and it was one of those, someone got burned by coffee things, and when the other lawyer got a hold of me, it got brutal. So, are you a coffee drinker? No. Have you ever had a cup of coffee? No. You know anything about coffee? No. Yeah, my expert testimony didn't go very far. Did you have a question? Oh, when I say it's not as strong, you know, if, let's say this is 5 newtons, and before, you know, if this was 2 coulombs, then this would be 2.5 newtons for each coulomb, so that this would be 5 newtons. And what happened was that, and this was a negative 2 coulombs, because these were in opposite directions. We just decreased this from 2.5 down to 2, and this got decreased down to 4. But that it's still negative, and so it's still going to be opposite the electric field. And this is still the positive plate, the negative plate, the electric field is still down.
Charge want to be attracted to the positive plate. So if the count kind of goes down to the negative plate, for negative, it's going to go up to the positive plate, the direction.
Well, the negative charge was in a field down, so it's feeling a force up. And that's what's getting weaker. If I've got less force up, but the same force down, it's gonna go that way. Yeah. Okay. That's the way they all feel. Yeah. Okay. Now, let's talk about this one. These plates are not hooked to a battery. They are insulated or isolated. And I find that this pitfall hangs like that. It hangs at an angle. And the question is that a positive or a negative pitfall? And then we're going to ask, well, first of all, let's answer that question. Is it positive or negative, people? Negative. It's negative. Okay. So now, if I move that negative plate to the right a little bit, is the angle going to decrease, increase, or stay the same? So please get out your clicker.
Yeah, going to the right, so there we go. think it would. Because if you're moving the right place closer, wait, it's gonna be more attractive, like. Let's see if the camera wants to- Oh. Oh, you're right, maybe it is look like. I don't know. I think it would still be, I think it would still be more because it's like. It's repelling it, yeah.
Okay. Last call, get it done, get your points. Okay, pretty good. The answer is C. Again, because these are insulated or isolated plates, the charge is stuck on the plates. And that means that the electric field between the plates stays the same. And same everywhere. And it's the electric field that's causing it to hang at an angle. That electric force is what brought it away from straight down. Okay, so the angle stays the same. Now, if I go back to your question, I just think I now realize what your concern was. If this is a negative charge, when it gets close to this negative plate, isn't it gonna say, ah? And that's the key, is no. The electric field strength doesn't get stronger when you get closer to the negative plate. It doesn't know that it's not there. It feels the same electric field here as it does up there, as it does up there. So getting closer to the plate doesn't mean anything. Okay. Okay. Let's look at problem 6.1. In problem 6.1, we're told that we have these parallel plates. We can call it a capacitor, if you will, and they're separated by 5 centimeters. And we're told that the electric field between the plates is 7,500 newtons for each coulomb. You're going to get a different number in your problem. But the first thing we're asked, well, when we say it's 7,500 newtons for each coulomb, we mean everywhere. You know, it doesn't matter where we look. It's going to be the same everywhere. Now, in an exam question, I might get tricky and say, well, the electric field is 7,500 newtons for each coulomb, right smack dab in the middle of the plates. What do you ignore? Right smack dab in the middle, because it's just everywhere is going to be the same. Everywhere is going to be the same. Okay. Now, the first thing we're asked is what's the voltage difference between the plates? So really quick, tell your neighbor how you would find that.
I think you do the, yeah, the ED equation, so the field times incidence.
Well, I guess you have the. That's nice.
Field is 7,500 times 5.
Okay. The voltage difference from the negative plate to the positive plate is going to be equal to the electric field strength times the distance from the negative plate to the positive plate. So that's going to be 7,500 newtons for each coulomb, but I can also write that we found as volts per meter. And then if I multiply that by how many meters I have from the negative plate to the positive plate, which is going to be 0.05 meters, that's going to give me 375 volts. Okay. Now, here's something that I find over and over again, people get confused about. They finally get it in their head that the electric field is everywhere the same, between those plates. But then they mistakenly go one step too far and say, well, the voltage is the same everywhere in there. No, when we say voltage, we mean voltage difference from some point A to some point B. If the voltage difference from here to here is 375, the voltage difference from here to here is going to be half that much. You know, if you think about what voltage is, I reach in my pocket, I pull out 1 coulomb, how much Vec do I have to do to get from here to there? If I have to do 375 joules of Vec to get all the way to the positive plate, I only have to do half that much Vec to get halfway across. Okay?
Would the sign of the voltage difference change if it went from positive to negative?
Oh, yeah, yeah, it's always highest near the positive and lowest near the negative. So from here to here would be a plus 375, and from here to here would be a minus 375. And you have to keep your wits about you to always remember, okay, which is the high end, which is the top of the cliff, which is the bottom of the cliff.
So then for this problem, do we know just to do the negative to the positive because like left to right or? Because it doesn't say like.
Oh,
positive.
I hope in the problem statement, let me just check to see. Oh. Maybe I will change that to say from the negative plate to the positive plate. Okay,
Thanks.
yeah, thank you. Okay. Now, that doesn't count as 2 mistakes on my part for all of y'all, just for him. Okay. Maybe he gets his tuition back if I make another one. Okay. Now, which plate, positive or negative, is at the higher voltage? Did we ask? Oh, sorry. Still getting the hang of that. Yeah, which plate, positive or negative, is at the higher voltage? So, yeah, I'll reword that. Not to worry. And let's get back to where we are. Okay. So the positive plate's at the higher voltage. Now, we fire a proton through a small hole in the negative plate straight towards the positive plate. And in that case, we're sending that proton where it doesn't want to go. We're sending it from the bottom of the cliff to the top of the cliff, and it doesn't want to go there. It's a positive charge. And so that means it's going to slow down as it goes towards that positive plate. Well, if it's losing kinetic energy, it's increasing its stored electric potential energy. We're cocking that electric spring. And so that means I would get a change in electric potential energy that is positive. Well, how big is it? Well, I know the operational definition of voltage says that the change in electric potential energy, as I go from the negative plate to the positive plate, is just going to be the test charge that's going from the negative plate to the positive plate. That's my proton, times the change in voltage from the negative plate to the positive plate. Well, that's going to be the elementary charge of a proton, 1.6 times 10 to the minus 19 coulombs. And the voltage we said was 375 volts. A volt is just a fancy way of saying joule for each coulomb. The coulombs cancel. And what I end up with is 6 times 10 to the minus 17 joules. Okay. Now, the last part of this problem says, well, what if I fired that proton with a speed of 2 times 10 to the 5th meters per second? That's pretty darn fast. Will it be able to get all the way across to the positive plate? Well, I know that if I started that proton out with this much kinetic energy, it would just barely get to the positive plate, kiss it briefly, and turn around and go back. This is how much kinetic energy I would need in order to make it all the way across from plate to plate. Well, let's see if we've got that much, okay? If I take that speed and plug it in here, I've got 1/2 times, it's a proton, 1.67 times 10 to the minus 27 kilograms. And this we said was 2 times 10 to the 5th meter per second. I got to square that. That gives me 3.34 times 10 to the minus 17 joules. How far am I going to get? A little past halfway. Okay. I just don't have enough kinetic energy to make it all the way across between those plates. Do a buddy check. Check your neighbor.
Are you good? No. You can't get to the other place. Oh, I get to, 10 to the negative 17. So I guess kinetic energy is less than what's required.
Okay. I have at the end of today's lecture, 5 problems that I think are helpful in getting you ready for the exam. Some are more difficult than others, and we're just going to race through those. And if we don't make it through all of them, I have placed the solutions in red on the slides so that you can go back and check to make sure that you get it correct when you're working it. Let's start with this one here. To what voltage difference must a proton initially at rest be accelerated to reach a speed of 5 times 10 to the 5th meters per second? Do you expect a positive answer or a negative answer? Tell your neighbor real quick. A positive answer or a negative answer?
Also if it's speeding up, it's going toward a negative amount. Like, so it's. Actually, I'm gonna use what describes positive or negative. I was gonna have to go to the.
Okay. Let's work it at the board. We start these voltage problems always the same place. Varric external is equal to the change in kinetic energy from initial to final, plus the change in electric potential energy from initial to final. And it's a proton, so we don't have to worry about the gravitational energy bucket. And because it's a proton, we can't do any external Varric on it. So this is going to be kinetic energy final minus kinetic energy initial is equal to minus the change in electric potential energy I can write as the test charge times the change in voltage. And let me just write that in a different color. Because that's what we're looking for. That's the goal. Okay, we're very quickly just going to turn this into an algebra problem, and we have to keep straight what it is we're after. Okay, and I put there it is. So it starts from rest, and my kinetic energy final is 1/2 times the mass times the speed. We wanted this to be 5 times 10 to the 6 meters per second. Gotta square that, remember to square it. Minus 0 is equal to, this minus sign is important. 1.6 times 10 to the minus 19 coulombs. And then we've got what we're looking for. And since this is positive, and this is positive, that minus sign, that minus sign is the zero sum game, where if this is a positive number, that's got to be a negative number, okay? And because of that minus sign, this had better be a negative answer, because the left-hand side's positive. You see that?
Yeah.
And when I solve for that, I get a delta V change in voltage of negative 130,000 watts. Okay. And carrying this around was not a good idea because I clicked it when I didn't mean to. See what I said? I put the answers in red. Okay. Ready for the next one? Yes, Greg, let's go, 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 go. A pair of parallel conducting plates with areas of 0.09 meters squared are charged to positive and negative 5 times 10 to the minus 8 coulombs. The plates are fixed 1 centimeter apart. If an electron is released from the negative plate, at what speed will it strike the positive plate? Well, I got to tell you, we don't have to erase much, okay? We're still releasing a particle from rest. Our Verk is still 0. Our initial kinetic energy is still 0. I can just... But now, I'm going to put this in black. And it's from the negative plate to the positive plate. So this would be at the positive plate, and this would be the negative plate. Now, if I plug in for kinetic energy, I have 1/2 times the mass of the electron, which will be on the front page of the exam, 9.11 times 10 to the minus 31 kilograms. And now I'm going to put the speed that it has, oops, remember, got to make that curly. The speed that it has when it reaches the positive plate, remember to square it. I'm subtracting off 0 there. And then, again, all the minus signs matter. This is an electron, so I have to put a minus sign here. And that's going to be 1.6 times 10 to the minus 19 coulombs. And, oh, we're in trouble. We need to know that voltage difference. We need to know that voltage difference. Well, we can find the voltage difference from the negative plate to the positive plate if I know the electric field between the plates times the distance from the negative plate to the positive plate. Well, I know that this is 0.01 meters. I need the electric field. Well, the electric field between the plates is just sigma over epsilon naught. Now I need sigma. So sigma is going to be the charge on one plate. Let's take the positive plate, 5 times 10 to the minus 8 coulombs, divided by the area of the plate, we're told is 0.09 meters squared. And that's going to give me a sigma of 5.56 times 10 to the minus 7 coulombs per meter squared. Now I calculate the electric field by taking that sigma and dividing by epsilon naught. And we know epsilon naught's just a number. And that's going to give me 6.3 times 10 to the 4th newtons for each coulomb. So if I bring that up here, 6.3 times 10 to the 4 Newton per coulombs. I could actually write that as volts per meter. The meters cancel. And what I get is 630 volts. So I bring that over here. And now it's algebra. It's just plug and chug. Okay. If I solve for that, what I get is 1.5 times 10 to the 7 meters per second. Okay, make sure that you're able to do the algebra to get that answer. If not, you need to practice algebra. I will point out that you want this minus sign here. If you want all the minus signs, because if you're missing one of the minus signs, you're going to take the square root of a negative number and your calculator is going to explode. There's going to be shrapnel all over the room. Okay. The minus signs are important when you're doing algebra. Let's go to the next one. Two small identical conducting spheres carry charges of plus 5q and minus 1q respectively. They're originally separated by a distance L. They are brought together so that they touch and then return to their original separation of L. What is the ratio of the strength of the force on either charge after they are touched to what it was before they were touched? Let's use our clickers one more time and see if we can figure that out. Okay, whenever you're ready, you can click.
Yes. Because I remember. On the yeah. I don't know if you take the average. Because I'm around 2. Yeah, it's really not. It was something that you added together, so I minus 1. I don't know what 5. I don't think it would be.
Okay, last call, please. Whoa. You do not want this question on your exam, do you? Okay. So let's solve that together. You remember when I have 2 point charges, the force between them is, I can write it as Q test times E. And I know that E is K times Q source over R squared, and that essentially just gives me K times Q source Q test over R squared. Well, we're not going to make a big deal about which one's the test charge or which one's the source charge. So we're just going to say, if I take the product of Q1 plus the product of, or the absolute value of Q1 multiplied by the absolute value of Q2 over R squared. And in this case, R is L. Okay. So I want the ratio of F new over F old. Well, F old is going to be K times I've got a 5Q. And I've got the absolute value of -1 is gonna be 1Q. And so that's going to be 5 KQ squared over L squared. Now, if I want F nu, I have to know what happens to those conducting balls when they touch together. Well, I had +5 and a -1. When I bring them together, the charge is free to commingle, to move where it's happiest. And I have a total, +5 - 1 is going to be a total of +4Q. And when I pull those apart, because they're identical metal spheres, there's no reason why one's going to get more than the other. And so I'm going to get 2Q on this one and 2Q on that one. And so that means my force nu is going to be K times 2Q times 2Q divided by L squared. And that's going to be 4KQ squared over L squared. Now, the F nu we said was 4 times this KQ squared over L squared. And the old one was 5KQ squared over L squared. This all cancels out, and I get the answer, which is 4/5. Okay,
I just knew.
so if you chose 4/5, kiss your own forehead. Okay. Next one. 3 equal positive charges are at the corners of an equilateral triangle. Point P is at the midpoint between two of the charges, Q1 and Q2. The electric field of P is, those are your choices. 0, not 0, but it's directed along a line from P to Q3. Not 0, but it's directed along the line from Q2 to P. Not 0, but it's directed along the line from Q1 to Q2. E, none of these is correct. So for those of you that are visual, let me draw a picture. Okay, so got 3 positive charges at an equilateral triangle. And point P is between 1 and 2. So with your clicker, one more time.
I remember the question. Because 1 and 2 cancel each other.
Okay, so this would be option B, this would be option C, and no. This would be option C, and this would be option D. So let's see how we did. Last call. The answer is E, none of the above. Okay, so. Folks, we don't have enough time to do this last problem. Actually, I've got 2 more problems. I lied, there's 6. So do those on your own and, the answers are on the page. Good luck on the exam. We'll see you tonight at 7 o'clock. Be there, be square.
That makes sense. I may try to go to the liquor tonight. I will not make.
Yeah, the field is gonna be pointing